Hello everyone, my name is Marvin and today I will present to you the Chai craters in historical aerial images dataset that we propose at WACV 2024. So the final World War II air raids were about 80 years ago, however unexploded ordnance is still a very major risk in construction projects, and even though many of the unexploded bombs have been found during the time and until today, finding UXOs is still very important, so you can do special precautions for construction and experts can sort of survey a very specific area instead of having to survey the whole area of the construction project. So why do we not just search for the unexploded bombs? Well, the reason for this is that it's not always very easy to find the unexploded bombs. So here you can see 7 bomb craters, and we know that about 10% of the bombs did not explode, and we also know that bombers usually had around 8 or 16 bombs. As a result, if we find 7 bomb craters like here, we already know that there's very likely an unexploded bomb, but the question is this the unexploded bomb? Is it this? Or is it this? And well, we know, and it was actually found that this is the unexploded bomb, but you can see its average size is like 3 pixels, and it's basically impossible to find. And so our goal is to find the unexploded bombs by finding the craters first, because they are direct evidence for the existence of of unexploded bombs. And in other cases, like in this case where it's just impossible to find individual unexploded bombs, these risk maps that we can estimate from the craters is sufficient enough so that the construction process can have specific security and safety guards in place. Okay, so let's start with an overview of the dataset. As you can see, it contains data from Austria and Germany. Our training data is from Graz and the area around it. It's about 50 images and 15,000 craters. Our validation data is from Linz and Vienna, and our test data is from Germany. In total, we have 99 images and about 20,000 craters. The annotation was not performed by us. The annotation was performed by our industry partner, Luftbilddatenbank. They have 12 years of experience, about 2,000 projects in Austria, and they are experts in Central European history, so they know and they have the documents when was an airstrike for which area. But they're also experts in analyzing historical aerial images. So yeah, each image is annotated by one expert, and then it's reviewed by 1 to 2 experts depending on the complexity of the scene. The dataset was prepared by us then for training. The first thing we did is we masked the region of interest, because the experts only annotated within the region of interest and not outside. And then we split the larger images into patches of 960 by 960 pixels with a 20% overlap. From this, we derived 2 datasets, the full dataset and the light dataset. The full dataset has 15,000 patches, and the light dataset is about 5,000 patches. The difference between both is essentially that in the full dataset we just take every patch that we extract from the dataset. So top right you can see some example patches, and in the light dataset we only keep patches that also have an annotated crater in it, which obviously reduces the amount of patches we have overall. And then you can also see here some examples from the dataset. What we found during our preparation of the dataset is that the annotation process, that there are some inconsistencies in the dataset. So first, the annotation process resulted in some ambiguities because it's designed for efficiency. We don't really know which annotation relates to which image. We just know the georeferenced image and the georeferenced coordinates of the bounding box. And as a result, about 5% of the annotations in our dataset lack visible craters. However, we, under the supervision of our industry partner, removed all of the ones that lack visible craters. For example, in the top left, you can see one bounding box that does not contain anything. However, we kept all of the things that still showed some remnants of the crater. So for example, top right, you can see an image where the crater has been filled in already, because obviously a crater is very ugly in your field. So as a farmer, you would fill it in already. But we kept it because it's still clearly visible that there was a crater, and an expert would also annotate it. Then there's also some inherent variability among the human annotators that was a bit of a challenge. Some draw the bounding boxes more tightly than others, and others just draw it very, very loosely and include also the ejector from the crater. And we found that about 10% of our images contain such inconsistencies. However, it was not all of the bounding boxes in an image that were a bit inconsistent, but more like there were clusters of them. Also here we resized the bounding boxes accordingly, and then had feedback from our industry partner whether or not these would be valid. So with regards to the baseline, we test 12 object detectors, some well established, some are from the state of the art, and some are from some directly remote sensing designed object detectors. And what you can immediately see from the results is that the object detectors designed for remote sensing, they perform very poorly. We expect that it's due to the fact that both of these require oriented bounding boxes, and oriented bounding boxes, while it does make sense in remote sensing, it does not make too much sense with craters, because there is no correct orientation for a crater. So learning that is probably very impossible, and therefore the performance of these object detectors is just significantly worse. But what you can also see is that all of the object detectors perform relatively similar, but there's a huge gap between the intersection over union 50 and the intersection over union of 75. We expect that this has something to do with the bounding boxes not being perfectly in size. However, we also think that the majority of the problem stems from the fact that the objects just are very, very small. The crater is usually 8 by 8 up to 20 by 20 pixels large, and therefore if you have a bounding box that is off by 1 pixel, you already reduce your intersection over union significantly. And you can also see that Dino is the best performing model here. However, I want to note that this Dino is not the self-supervised Dino. Instead, it's the data with improved denoising anchor boxes for end-to-end object detection from Zhang et al. Because there was some confusion before. Yes, this brings me to the visual analysis. So in rural areas, you can see that that model Dino performs basically perfect. In an urban area, you can see that it doesn't detect anything in this example. However, it confuses these, I believe they are storage tanks or some sewage cleaning stuff. These are incorrectly detected as bomb craters. And then there's also the problem of a different domain. So in this case, we have a snow image. Snow images are part of the training data. However, there are only one image in the training, test, and validation data set part that contains snow, so it's not a very known domain to the model, and you can see here that 2 of the craters are detected with a very high confidence, however 2 are not detected at all. Yeah, so this brings me to the conclusion. We presented today, or we will present a unique historical data set which contains 99 images, about 20,000 bomb craters. We also showed that you can achieve a reasonably high baseline performance in the intersection over union 50 metric. However, we also showed that the mean average precision with the intersection over union of 75 is not high enough for deployment. And we also showed you some dataset limitations. The dominant one is the other domains are very challenging, like snow, and also that the accuracy in urban areas drops strongly, and debris and human-made structures are also very challenging. Thank you. If you want, you can shoot me a mail. Otherwise, I'll hopefully see you at WACV.